Here we go. How we doing, everyone? There we go. That's our little nail. Let's get rid of that. Oh yeah, I was teaching some classes here. You guys want to learn about Laplace transforms? Heck no. You guys are learning circuits.
And what class is that for?
Signals and systems class. That's what we do. Let me see.
E360.
Yep, it's one of our courses here. Let me see if I could show you. Yeah, that's me right there. That's my projects, courses. This is one of the main ones I do here on the campus. We go over signals and systems, and basically here in this class we tell you cheat sheets. In this class you don't know that until it clicks. So that's a hint for later. The juniors are all crying, or I don't know, maybe they're happy. They just got their exams back today. Anyways, we're here to talk about circuits. So how are the classes going? How's everyone's lectures? Good, bad? How's the homework? Painful? Fun? Not enough pain? Too much pain? Want me to complain to your professor saying, man, they're having an easy time. We should bump up the temperature. Anything else? Let me see. What are you guys talking about in class?
Right now we're learning about, we were doing capacitors. We were learning about capacitors and what else? RLC circuits.
Finally got to inductors?
What's that?
You guys got to inductors already?
Yeah, inductors.
How was that?
Not that bad.
Okay.
I think so.
Let me just check that. So you guys are recalling that, okay, so you know what an inductor is, right? It's just this funny wiggly line, right? Just a coil wire. Or if I wanted to draw it something even better, here's like some metal, right? Some iron core, and then you have some wire that's just looping around like this, right? Boom, like that, plus minus V. Is that correct?
Yeah.
What's the equation that they told you had to memorize?
Something dV over C or dt. Yeah.
For an inductor, right?
Yeah, I'm trying to catch up here because it's very similar to the other one.
And then for the capacitor, right?
Yeah, because there's two of them,
capacitor.
right? They're like kind of similar.
It's just, I don't know, just a square right here. 2 plates. There's another square. And then you got some space, or D, and plus minus, right? And then you know the current in this one here, right here, right? Is I is equal to C dV over dt. Is that clicking in your minds?
Yeah. I remember those, yep.
And how are we doing with the homeworks? Are we getting them good? Are we understanding what's going on? Yes, no, maybe? I don't know, man. I haven't started.
I'm going to start it today.
Okay, so what do you guys want me to do?
This class.
What do you guys want me to do? So have you guys seen them both in action with like RLs and RC circuits? LR, or I don't know. I call it RC circuit. Some people call it's called CR. I'm like, it's the same thing, man. Or LR, RL, RLC. It's just a way. And then there's another circuit called an LC circuit. I'll show you what that means.
Yeah, RC versus RL.
You guys know what this is? Who's my electrical engineers here? Yeah? You guys know what happens when you put these two together? It's called a tank circuit.
Tank circuit. Yeah,
so it's going to have a resonating frequency, okay? Well, you won't know that. That's a surprise tool for like next semester. What happens when you put them in parallel? Or just, do I want to talk about it? Let's go over fundamentals, okay? At DC, right, or let's just say it's a constant voltage or constant current, right? I is equal to, I don't know, something, right? It's constant, right? And I have time goes to infinity, right? What happens with the inductor? Come on. It's just a wire, right? It's just going to look like a piece of wire. It's just going to be like, oh, just a wire. So that means, what does that mean about the voltage? Plus minus V. If it's a wire, shorting the plus and the minus. right? Does that make sense?
Yeah.
Why? Because it's just a wire. The inductor is just a piece of wire. It's just this coil of wire, right? Try shorting the plus and minus of a 9-volt battery. See what happens. Shorts. Boom. Anyways, what happens if I have, what do you call it? Because then I have to introduce you high frequencies. You guys haven't gone over frequencies, right? Sinusoids, no sine waves.
No.
Okay, so I'll tell you this. This doesn't like it when you change the current. All right, it hates it changing current, but this one loves changing current, but hates changing voltage. Right, so you'll start seeing that this tank circuit or this capacitor, well, this right here, it doesn't want to change anything, so it's just an open. But this one, well, if you have an empty bucket and you're just shaking it up and down, right, you're going to realize, well, the voltage is also going to be zero, but I won't tell you that until, well, you guys understand what do you call AC analysis is. But don't worry, this is a tank circuit, nothing you need to know for now, or maybe, it depends if you want to stretch your main. So, what do you guys want to do today? What homework problems you want to try? What LT Spice? How's LT Spice going?
I like playing with it.
Yeah, it's fun, right?
It's kind of cool because you can like visually see stuff.
Yeah, and it's helping you.
It helps you a little bit better. Like I noticed, like with this class, like when I studied electronics in high school, like we did a lot of hands-on stuff.
Okay.
So like you actually see the pieces. But, like with the circuits, LT Spice helps because with the schematics, like it's just you just get a better understanding. Like,
Okay.
you can see it a little better, like in action, instead of just seeing the picture. So you actually kind of see how the current and how the voltage is running through the circuit visually.
Mm-hmm.
I guess you can. That's what I'm trying to say.
Okay. So let's see. How's the homework? So, well, you guys are starting that right now. Any problems you want to go over? What about who did we go over last week? Did we go over Dr. Zoo's, or was it Pushkin? Forget. I think it was. I don't remember. Let's just go over the homework. Let's see. These are the problems I copy pasted. 16. Is this what we did last time? I'm hoping we don't. 16. Let's see. 16. This is 14. 15. 16. Determine the voltages. V1 to V3 in the circuit. This one right here. Does everyone know how to do that? No? Yes? We're confident? You guys know how to simulate that? Let me just show you.
Let me see. Let me look at my notes because I know he did a couple problems, Dr. Pushkin.
Mm-hmm.
But I like record my lectures or whatever.
Okay.
So and I take pictures. So here, let me open this up because I know he covered a couple of those, and he was like showing us different kind of like shortcuts. Because I know that's what we covered today, like using the derivative.
Okay.
Instead of like the way the book shows you to like use all these long equations, like he showed us a shorter way. I don't know I can't think off the top of my head. I have to go back.
Let's just do a quick test, okay? See if I can do it. Resistor, capacitor. Don't worry, I'll flip it up. I hear everyone complaining. Can't see, David. We can't see. I know, I can't see either. That's why I have glasses. Anyways, plus, minus. This is V2, 20 UF. This is also 60 UF. Don't worry. I'm writing it. V3 plus minus. This is 3 ohms. 18, 4 plus minus V1, 10 U. This is 10 ohms. This is 40 volts. This is 6 ohms. 6 ohms. 6 ohms. There we go. Can't draw my 6. Does that look good? All right. It's saying what's the voltages at the capacitors under DC conditions. Now, trivial question.
What number was this you're doing?
516.
Oh yeah, he didn't do that. He did 17, 14.
Yeah, because he expects you to do the other homework, right?
Yeah, so
yeah, you see?
16. Yeah, no,
giving you guys your money's worth.
Got you.
You like it when the professor does homework or doesn't do your homework? Yeah, I want to do homework. We're doing your homework anyways. What's the first thing you do in this circuit? Come on. Well, okay, you're jumping a step, but I was gonna say just draw your reference, right? Easy, right? Boom. What's the voltage here?
0.
0. Okay. Well, congrats. 2 points right there, right? Or I don't know how many this thing he's trying to do. Then the next thing, yeah, which is just to treat all your capacitors as opens, okay? So what do we have here? We have this guy right here, right? And then we have this guy right here. That's going to be 1 voltage. Then this right here is going to be another voltage, right? And this right here is going to be another voltage. Is that good with everybody? Let's redraw the circuit. So what do we have here? We have, well, in order to draw this, plus, minus. Got a resistor right here. Got a resistor. Got another resistor. My little ground. 40, 10, 18. 4, right? We just said this is an open, right? If I were to go this way, correct? It's an open, right? Nothing, right? Good. Then we also said going this way, it's also an open, correct? So we can ignore that, don't worry. Then we have this guy right here, 3 ohms, right? And then what did we just say over here? It's an open, right? So we got plus minus V1. Good? And then right here we have, well, you're going to have this invisible wire right here. I'll show you what I mean. Plus minus V or V2, right? Plus minus V3. Good. And then we have some resistor over here, which is 6, right? Is that looking clear?
Yeah.
So let's just solve for the circuit. What's going on? Let's see. So we have this circuit right here, right, or whatever this current. Let's just draw them. Wants me to use yellow. Can you see that color?
Yeah.
Yeah, it looks like gray. It's kind of like yellow, you see? What's the current in here? Trivial question. 0, right? It's an open, right? What about the current in here? Or if I were to draw this big super circle. There's going to be a current in there, right? You got this 6 ohm resistor, right? And 3 ohm resistor, right? In parallel, right? So what does this mean about these 2 resistors? Well, actually, wait, they're not in parallel because we have this right here. That makes it even tougher. Okay? So let's do it. Let's see. What's our next thing we got to do? Well, if you think about it, let's think. This right here is in series. You see how this right here and this right here are in series, right? 6 plus 3, right? Gives you 9. And then this right here is our 18, right? If I were to redraw like this, I'm going to use a different marker. I don't like this one. Here's the 18 ohm resistor, right? 18, right? Here's our 6 ohm, right? 6 ohm resistor, right? And then that 3 ohm resistor, right? Redraw it like that. Goes down to the 4, right? Is this looking better? You guys like that circuit? Feels good? Then what's the voltage over here? Well, based off this, got this V2, right? Plus, well, then we got this line right here. 18. Hear me out. If I were to do this, right? Right? This right here is plus minus V2, right? Plus minus V3. No, wait, no. I drew this wrong. This is right here. Here's my 6 ohm resistor, right? Oh, wait, no, wait. I think I did it right. Because I'm going from this 18 right here, from this right here. I'm cutting the 6 right here. Oh. Let me just see how I can do this. Because if we simplify it to this, you just get, you see this node right here? If I were to draw this, this is what I'm trying to do. I'm trying to simplify just this circuit right here, okay? Is that making sense? Right? What's the resistance for this? This right here is going
to simplify that.
Yeah.
Where the 2 capacitors are in parallel with the 6 and the 3.
So I'm trying to simplify this so we can start solving for our voltages.
Okay.
Okay. This 6 and 3, right, in series, right, makes 9, correct? Then I have 9 and 18, correct? In parallel, what does that equal? 9 times 18 over 9 plus 18. What's that equal? Calculator. So if I have 9 times 18, right? Divided by 9 plus 18 is 27, right? 6 ohms. So this whole thing right here is a 6 ohm resistor. Oh, sorry. Is that making sense right there? 6 ohms for that whole thing? This is page 2. Okay, now let's rewrite this circuit so you guys are in line with what's going on. Don't want to take too much time on this problem. Okay, anyways. Let's rewrite that circuit. I know, it's a lot of work. Resistor, plus minus, 40, 10. And then we just replaced this resistor with 6 ohms. And then 4 ohms right here, or 4 ohms. There we go. Is that looking better? Because right now I'm trying to find the voltage right here, okay? Or better yet, what's the total current coming out, okay? Let's solve for the current. What's the total current in this? What's V equals IR? Or it's going to be I is equal to V over R. What's our total voltage?
40.
What's the total resistance? 10 plus 6
10
plus
6 plus 4.
right? So
We're
that's
looking at
40 divided by
amps.
20. Yep, 2 amps.
Yeah. And that's just for that little part you simplified, right?
Yep, so now we have the total current coming out of our source, okay? So now the next thing is, well, let's just see. I want to know what this voltage over here is, right? Because then I can get, well, this other voltage right here and this other guy. We'll see what we can do. Let's redraw this. I'm not liking this. Okay, plus, minus, 10. And then let's just see, how do we want to simplify this? 18 ohms. 6 ohms. 3. There you go. And here's our 4. I'll just put these plus right here. Is that looking good? And we already know the total current going here, right? It's 2 amps, right? Is that good with everybody? So I think the next thing we want to do is, well, we want to solve for all these voltages, right? So let's just see. Well, if I went back to this example right here, right? Here's, let me just use color codes. Can you agree that this point right here is the same thing as this point right there, right? So we can solve for that voltage, right? If I were to solve for this voltage divider, what's the voltage over here? I'm just going to call it V out or VY or whatever. What's that voltage? Who knows the cheat way? Our input voltage, right? Times that resistance we're trying to find, that voltage drop, plus, minus, right? Which is going to be 6 plus 4, that resistance that we're trying to find, right? The voltage drop of that resistor, or these two resistors in series, right? Then all this plus or divided by the summation of all the resistors. So that's going to be our 20, right? 20 ohms. Is that good? And well, we got 40 times 10, all divided by 20. Well, this cancels out. Then we're left with, well, 40 divided by 2. What's that equal to? 20 volts. That look cool? What does that mean about this? We just lost half our voltage going over here, 20 volts. Is that making sense with everybody? Any questions about that? And now we just want to know, well, what's the voltage? Let's see, if we have 20 volts over here, and then let me see, well, what's the voltage over here? Okay, all right, let's just use another color. Can everyone agree that this point right here, right, is this point right here, right? So we can solve for that voltage divider again, right? Right? I'm going to call this one Vx just for whatever labels, okay? What's the voltage over there? 40, right? Our input voltage times what's our voltage drop? What's the resistor we're dropping? 4, right? Over the total resistance, 20, right? So that's going to be, let's see. Well, 4 and 20 give you 40 divided by 5, right? Which is giving you 8 volts. Is that good? So our voltage here is 8. Is that making sense? Now let's just see. If we have 20 volts over here and we have 8 volts over here, we can technically solve for, well, we have the currents going through here. How do I want to try this? Let's see. Because I want to show you something cool. What's the current going through this 18 ohm resistor? Let's call it I don't know, IA, whatever. Got that 18 ohm resistor, right? It's going to be, what's V equals IR, right? V plus minus V minus, right? 20 volts minus 8, right? V plus minus V minus divided by that 18, right? What's that equal to? 12 divided by 18, right? Which is equal to, hopefully it comes down to a nice number. 4/3? Huh? 2/3?
2/3, okay.
Right? So can we agree that, okay, we have 2 amps coming through our source, correct? And then 2/3 of the amps go this way, right? So what about this path right here? How many amps are going through here? If I were to call this one IB. It's going to be the I total, right, minus IA. What's our total? So let's just see. That's 1 plus 4 over 3. Is that making sense? Cool. But now here I want to solve for the voltage right here, okay? I want to know what this voltage is, right? What's the voltage over here? I'm going to call it VY. Are we getting lost with all these variables? Nope. We already have IB, right? We have a resistor, right? We have the voltage right here, right? What's the voltage over here? VY? Well, we have 20 volts, correct? 20 volts, right? Running man, remember the running man? We're starting right here at 20 volts, right? Cool. And now I'm just going plus minus down the stairs, right? By that current times that resistance, KVL, minus. Anyone bothered if I do this? 4 over 3 times 6. Is that good with everybody? What was that equal to? 20 minus, well, got this 24 divided by 3 is 8. Is that good with everybody? 12 volts? Did we get that in homework? Is that good with everybody? Nice. Let's do this one more time because I think I'm seeing blank faces. Or not. Maybe you guys are thinking really smart, like, man, this guy's so slow. That's okay. Let's go. Plus minus. Right there. We've got to solve our circuit itself. Just put that right there. Put that right there. Resistor. Boom. Oh. Ignore this. I don't like that. Anyways. This is what I get from being messy. I don't like messy work. Okay, let's try it again. There we go. Resistor. Resistor. Terminal. Okay. Resistor. I'm going to put a terminal here. Another terminal over here, just in case. Resistor right there. There we go. A lot better. Okay, now let's do our established voltages. We just established that the voltage over here was 20 volts, right? The voltage over here was 18 volt, or not 18, 8 volts, right? Is that good? The voltage here was 12 volts. Is that good? It's 40 volts, right? And then this right here, what's the voltage here? 0, easy. So let's look back at our original problem. Problem states we need plus minus, right? Plus minus V1, right? If I were to go back over here, plus minus V1. What's the charge over here? What's the voltage over here? 0. What's the voltage over here? 12. What's the voltage drop? Is that good? Any questions about that? Now let's do this other one. Let me see. Because now I'm wondering about these two. Well, I'll tell you this. If you do the following, you got plus minus, plus minus. Plus minus V2 capacitor. Plus minus, or V3 minus. Right? Let's just call it, let me see. I want to give it to you guys an easier way. I don't want to try this. Because I want this, believe me if that's, the voltage here is 20, right? 20 volts right here, right? And the voltage right here is 12, right? And I'm trying to find that total voltage drop, right? If I were to create some, let me just do plus minus, right? I'm trying to do some mega voltage, VC, correct? Right? VC is going to be 20 minus 12, right? What's that equal to? 8? Which is going to equal, right? Plus, well, V2, right? V2 plus V3, right? Is that good with everybody? Now let's see. Have they taught you about charge? What charge sharing? You guys know what charge sharing is? Let's try. Let's try this. I'm trying to see how do I want to show you this. All right, this is going to be a special topic. I'm going to do an emergency thing. We're going to create our virtual ground. I'm going to do like a virtual probe. Can everyone agree that the voltage drop between this and this is 8, right? Let's just say this. Okay, I'm going to pull your brains out right now. Let's just say this ground right here, I'm going to add 1,000 volts, right? What happens to everything here, all the voltages? Goes up by 1,000, right? It's constant, correct? Does that make sense? This reference, it's just something to help us, okay? So imagine if I'd made like some kind of ghost reference here, right? Some like, I don't know, virtual. To help. It's just to help us mathematically, right? If I force this to this 12 volts to 0, okay, right? Now this is our new 0 volts, okay? Is that making sense? So I'm putting ground over here, right? And now this 12 all of a sudden is now, well, it's now 0, right? So what does that mean about everything else? Everything also goes down by 12, right? So what happens with the voltage over here? It's going to be minus 12. So everything starts pushing down. So what I'm trying to say is you see this 20 volt, right? Based off this new reference, I'm calling it. What's the total voltage through here? 8. Making sense? The voltage differences is what matters. It doesn't matter about this reference. Your reference could be, I don't know, a kilovolt. But then you have like 1.2 kilovolts. Well, your voltage difference is 200 volts. But it's the difference that matters, okay? Your reference is what's going to help you out with this course and your entire EE degree or ECE degrees, all right? So what I'm going to try and do is I'm going to create a new circuit just to demonstrate. Plus minus 8 volts. All right, and this right here is what capacitor is that? is going to be our V2 plus minus V3. Let's see, 20 micro, and this right here is 60 micro. All right, let me see if I remember how to do charge sharing. And we want to find this V out, right? It's the voltage there. Remember how voltage drops work with capacitors? It's like when you have capacitors in series, right? Or in series, it acts like a parallel resistance. So let me see if I remember how to do this. V out, and I have this 8 volts right here, and I want to divide it sharingly. Let's see if I remember how to do this. We have this capacitor here. That's our voltage divider. Let me remember, because I'm not remember this one. But the point is, this one's gonna have a heavier charge than this guy. That's what I'm trying to figure out. The question is, we're sharing charge. Let me see. Is that something he taught you guys in class? Charge sharing? No? Our charge sharing equation. Let's see if there is a picture. Ah, there it is. Well, that's not what I want. No, I want 2 capacitors. 2 capacitors in series, because this right here is technically charge sharing. We're just sharing the charge, where you're looking at the voltages. Looks like we're gonna have to do this the raw metal way. Q is equal to CV. Let's see what I can do. Let's see. Well, you have a voltage here. Let's recall Q is equal to CV, right? Where we know we have some capacitor, some voltage, and we have some charge. It's going to be V2, C2. This right here is equal to C3, V3, right? And I'm going to have some total voltage right here. So let's just see. If I 8 volts and I'm trying to share it. Let me remember. Nah, I'm not getting this one right here. This one's important. How to share charge.
Wouldn't it just be like direct ratio, like 20 over 60?
That's what I'm thinking too.
So it would, yeah, so it'd be 1/3, 2/3. What equal 8?
Yeah, that's what I'm thinking too, because technically this is a bigger charge or bigger tank, right?
Yeah.
And this one's a smaller capacitor, but this one should charge, well, let's just see the simulation. That's where I like it. LT Spice. I know there's an equation out there, or not an equation, there's a way to derive it. But everyone knows how to use LT Spice now, right? Everyone's been using this to help with your homework. Okay, let's see. Boom. Capacitor, boom. Boom. Resistor, boom. Another resistor right here, boom. 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 Voltage, right? Straw circuit, boom. You guys like my orange lines? You can change this in the color panel. Okay, I got our capacitor here. Draw this big fat box because that's what I've been doing all this time. Oh. Wire, boom. This is where LT Spice can help you out. Okay, what's our resistor here? Is our 10 ohms. Right here is our 40 volts. Base was 18 ohms. This right here is 4 ohms. This right here was 6. This here was 3. This here was 20 micro. This right here is 60 micro. And this right here was, what did the textbook say? Let's see. Circuit 10 micro. All right, we want to know what, I'm going to call this one V out. This right here is going to be called V, I don't know, what was I calling it, VY or VX? Yeah, let's call it VX, whatever. And this right here is VY. Everything's marked. Let's run it. 1 second. Let's see what happened. Do we get 20 volts? Oh yeah, we got 20 volts, right? How about the voltage right here? 12 volts. VX, 8 volts. So what's the total charge over here? You can do the following where you can go to your thing. Well, if you do this, hold and drag, you can get the following voltage like this. Or, it's not letting me do it. There you go. Aha. Minus 12. Let me just delete this. Did everyone see how I did that? Okay, when you click on a node, right, it does plus to minus. Negative V of VY, right? 12 volts. Is that cool? Now we want to know what this is right here. I'm going to call this one, I don't know, V mid. Okay, rerun. Okay, plus to minus. All right, who's ready? What's that voltage? Oh, Control Z. What is that voltage? 20 volts. Really? 20 volts. What about this one? From here, plus to minus. Minus 12 volts. Huh, what's going on? Okay, let's do something else. Plus to minus, this should be 8. 8. Yes, that's 8 volts. This right here is 8 volts. So what happened over here? This right here, if I did this from here, right, from V out to V mid, right, I'm getting 12 volts, minus 12 volts. Are you guys seeing what I'm saying right now?
Yeah.
The heck? So it's saying, I don't like this. LT Spice is saying V2 is equal to minus 12. Minus 12, yep. And then from V mid, that's what I'm calling it, from V mid to VY. Wait, hold up. Well, let me try this again. Something's wrong. I don't like this. V out.
To do that, you just click and just drag.
20 volts, yeah. Plus 20 volts in V3. Yeah, so what I did right here, let me show you again. Control Z. All right. I do this, V out, right? V out plus to minus, right? That's 20 volts, okay? So the voltage drop, the difference in here in this capacitor, there's 20 volts in this capacitor.
Wouldn't that mean it's charged?
That's making me wonder too, and I don't like that. You know what? I'm going to do the following because I'm not liking this at all. We're going to have to set everything to 0 charge. And you want to know how I'm going to do that? Because I don't like this. Let's do initial conditions. Dot IC V VY is equal to 0 volts. So what did I do right here? Is I forced this node right here to be 0 volts. So I have 0 volts here and 0 volts there, right? So that means 0, okay? There's no charge in there, all right? So if this right here is 0 volts, right? I need to force this to be 0 too, right? Right? Dot IC V of V mid, right? 0 volts. I'm gonna put a V in there. Good. Now the charge between this it's empty, right? Is that good? Dot IC V of V out, I'm just calling it 0 volts, right? So now we have 0 volts here, 0 volts here, 0 volts here. All the buckets are empty. Cool. Now let's get it to run. Whoa, let's see what happened. I think I like that. Maybe, I don't know. Let's see. V out, right? To here. That's our 8 volts, correct? V out plus to minus V mid. 6 volts. You like that? Whew, man, I was panicking. I was like, what the heck just happened? V mid plus to minus. What are we getting here? 2 volts. So 8 volts, we get split right here. This one takes the majority of the charge. The small capacitor takes more voltage than the other one. Why? Because when we have a smaller bucket, right? If I were to say this, how do I want to say this?
Because it fills first.
Yeah. How do I want to say this? Think of this water bottle. It's a small water bottle, right? And I have something big like the Starbucks cup, right? It's a big cup. It's a venti size cup, right? If I have, what do you call it? Think of your hose water from like the tap. Which one's going to fill up first? Smaller one, right? So the bigger one's not going to fill up at all. This one's going to fill up very fast to a higher level, 0 to full, right? But this one's going to take forever to fill it up. It's a big fat bucket. Think about a pool versus a small tube, okay? So that's why with the smaller capacitor, now you're realizing, the smaller capacitor charges up first because it's a smaller bucket. Does that make sense?
Now, what if they were flipped?
Well, let's test that. Let's do 60 microfarads and 20 microfarads. What happened? Let's do this. Boom, boom, boom. Plus to minus. It's 2 volts in our heavy bucket or big bucket, right? The big bucket is a very heavy bucket. It's not gonna fill up as fast as this capacitor right there. The smaller bucket, plus to minus, 6 volts right here. Is that making sense? Is this cool?
It wouldn't matter.
Yeah, thank you to the gentleman who told me hey, set the initial voltages, which is very true. You see what happened? So now someone's gonna be like, man, did you get minus 12 in that capacitor? What are you talking about?
Now, is that something we should always think about?
With capacitors?
Yeah.
When you're doing transients, most of the time, well, it depends. It's good to set everything to 0 charge because capacitors initially have no charge. There's nothing in them. They're just buckets of empty water. But you have to set that up first. Some circuits, it's not that hard, especially when you have a V out and a ground that are established. But this right here, it didn't know what to do. So the computer just said, I'm just going to calculate what makes it easier for me. Now we're going to make this computer work. And guess what happened over here? Yeah, it doesn't like that. You want to see the current? Boom. Look at that. Very fat charge. Yeah, heavy. Anyways, is that cool? But now everyone's asking, how do I actually get that calculator? That's what I'm trying to figure out too, man. Because let's see. Let's go back to our thing. Let's see right here. With IC equals 0, or what do you call it? Initial voltages equal to 0 volts. Now we get V2 was equal to, the smaller bucket got 6 volts, right? And V3 was equal to 2 volts, right? And then our gentleman said, oh, is it going to be 20 over 6, right? Right? We got 1/3, right? I think that's what I'm trying to think about because technically, I want to say it's this. You see this? I was trying to do this. This is our heavy capacitor. Something's telling me this. 1 over C, I'm going to call this C3, over 1 over C3 plus 1 over C2. Does Is that making sense what I was trying to do there? Let me do this on another piece of paper because I want to make sure you guys get your money's worth. Teaching helps the teacher learn with the students. That's why we need teachers to teach. Anyways, V, I'm just calling it V, whatever, V mid. That's what I was trying to do. 8 volts, 1 over 60, right? 60 microfarads, right? Over 120 microfarads plus 160 microfarads, right? Is that good with everybody? I'm trying to figure out this capacitor here because it's in parallel. Do you understand what I'm trying to say? Let me see. No, because what I'm trying to say right here, capacitor. Can everyone agree that this right here is C total, right? But I'm trying to do just this capacitor right there. So I'm trying to do something like this. 8 times C3 divided by C total to get that voltage divider, right? So if I were to do this 8 times 60, right? And what's C total? Which is this in parallel, and what do you call it? This series thing, and it's this equation right here. 20 micro times 60 micro, all divided by 80 micro, right? All the micros cancel out. Get 20 times 60, which is, what do you call it? Actually, better yet. Let's see. This 20 and this 80 give you the 1 over 4, right? And 60 divided by 4, what's that equal to? 20, no. 1, 12? No. Yeah, I want to mess up. 60 divided by 4. 15. Is that right? No, the micro. We're still left with a micro over here. There we go. 15 micro. Let's see if this works. Because I'm not liking this.
I have a way where they did it.
Okay.
You want to see it really quick? You might understand it more than me.
Yeah, I'd like to see it.
Here, I'll show you.
Does it take R equivalent?
That's what I'm trying to figure out too. Hold up. Give it to me.
Here, look. You might be able to understand this more than me. So we got here, right, where you showed us.
Yep. That's it.
So you got us here.
Yep. We got the total voltage. Yep. Keep going. Because I'm trying to find it's the capacitor. That's the more important part. Keep going. I'm trying to find V2 and V3.
And then that's where they got right here.
Yeah, that's what we got. Okay. Charge sharing. Q is equal to CV. Wait, hold up. It's saying assume the charges in the capacitors are equivalent. Oh, okay.
Yeah, that's what they got for like the final. It's 6 and 2. You're right. Like with LT Spice, but now you might be able to explain it to us better because I wasn't getting it.
That's pretty smart. All right, no, thank you. It's saying assume the charges in here are shared. So let's just say this. Capacitor, thank you very much. You see, this is where I'm trying to learn too. So there's this thing called charge sharing where thank you. We have some Q right here. We have some charge in here, right? But basically these capacitors want to keep the same charge like throughout the whole thing, like it's a one uniform capacitor. So basically it's saying the charge in V2, right? In capacitor C2 or QC2, right, is equal to QC3, right? The charges are the same, correct? But you remember Q is equal to CV, right? So we got to assume that the charges are going to be the same, okay? So if I were to do C2, right, times V2, right, is equal to C3, right? V3, right? Now I just got to solve for one or the other. Let's just do V2 is equal to C3 over C2 V3. All right? Remember that 8 volts, which is equal to V2 plus V3, right? Boom, what do we have right here? There we go. 8 is equal to C3 and C2. What's C3? 60, right? 60 micro over 20 micro, right? V3 plus V3, right? Or this one here is more 3, right? 8 is equal to, what do you call it? 60 divided by 2, 3V3. I get this right? 4V3, right? V3 is equal to 2 volts. Whew! And now plug this right here, right? What, solve for V2? Or actually better yet, you can just punch it in right here. V2 is equal to 8 minus 2. Woo! Man, bring you back to your physics days, huh? Is that cool? Were there any questions on how we did that?
See, that's why you come to class.
See, that's why you come to class. Hey, so this is something that my professor told me, and I'll tell you this. If you guys believe, well, okay, professors, they're humans too. We all make mistakes, and I'm trying to start my PhD as we speak. I think one of the mottos that I have from my professor, let me just show you. I'll just get off on a rant. Or not rant, but just talk. Just see, this is my professor over here. Return CMOS EDU. See if he has, what do you call it? I don't remember if he had, oh yeah, that's my professor. He goes hog hunting. Pretty good. Click on the image to play a video. No, the clicking is your choice. Oh yeah, pretty good professor. But one of his quotes was, I don't remember, but it's basically, yeah, research is great, but teaching also reinforces your knowledge too, so that you can better do your research. So that's what I'm also doing here too. So I don't have all the answers in the world, but I'm also learning. That's where I have the master's degree going to PhD. So in the end, this is why I appreciate all the comments and questions and concerns from the students, student feedback. I think you guys also have student evaluations coming up too, right? Yeah, so for this class, well, this is a discussion. I'm just doing my best to do whatever you guys need. I just answer questions and do LT Spice, all right? So, hey, take care there. Are there any other questions regarding the course or this discussion or just anything in general for the next 3 minutes? No? But yeah, anyways, no, this is good knowledge. No, it's you'll see this all the time. Or not all this problem all the time, but you'll see other things. Well, let's just check. Isn't this homework due in like 2 days?
14th at midnight.
Yeah, 14th at midnight.
Yeah.
But yeah, that was a good toughie one, okay?
Did he push it more? Did he push it again?
I think yesterday was today, and now it's the 14th.
Okay. Does everyone know how to use these governing equations over here? Right? This is a bad screenshot. Right? Easy, just plug and chug, like the last class we did last week. Yeah, it wasn't that bad. You just find your RC, and if you needed to, you can solve for a Thevenin circuit to find the total resistance so you can find that time constant RC. Is that good? Right? And then for those who are saying, hey, I just don't get it, and yeah, you can use, I don't know, ChatGPT or whatever you want, but there's also LT Spice to help you with getting your solutions, but it's not about, oh, I'm just going to plug and chug and get an answer, but I'm just trying to understand so I can get to, like, I don't know, to where I need to go, okay? So in the end, yes, this is all good, useful information, just the way you take it, so I'm just here to provide as much material as you want. So other than that, are there any other questions before we end? Yes, I'll give you the file. Any other final questions we have? Let's see. We'll meet again next week. It's F1 too, F1 racing. And then Wednesday, should we have a discussion that day? Or you guys want to go on Thanksgiving break? You tell me.
I will not. Probably won't be there.
Should we just cancel that day before Thanksgiving?
I'll probably be traveling.
Yeah, because I hear a lot of people canceling. So you want to cancel that day? Take a good day off? And then we'll have our final session December 3rd. That's study week. Well, technically, attendance is required, but there's no new lecture material. I'm just here to help.
Wait, when's our next test? Do you remember? We have one more midterm before the final.
No, it's,
3 midterms.
3 midterms?
Yeah.
So yeah, we'll just have one more right there. And then you guys are done with me. Unless you guys are taking 221, you'll see me again next semester as your lab director. Do a lot of cool stuff.
24th.
Remember
Yeah,
24th?
so we won't even, we'll be fresh out of midterm.
So yeah, technically, you're fresh out of it, so that means don't come then, right?
Yeah, Monday was our midterm, so Wednesday, I don't even know if we're gonna
You guys are steamed. Just go home. So anyways, we have next week. We're not meeting on Wednesday that Thanksgiving, right? And we have that Wednesday, December 3rd. And that's it. And then you guys don't see me ever again or whatever. No, just kidding. If you take 221 next semester, you guys will see me in labs. I've improved the labs as best as we can, but I am always making them a living, well-breathing document so I can get you guys your money's worth. So, and then if you take the next semester, promise me this, do circuits 1, circuits 2, circuits 3. You will never forget it. You can just dump all your information after circuits 3, which is our electronics classes, so that you don't forget your memory. If you do 320 in the summer, we won't do PCBs, but if you do it in a normal semester, we're going to do some cool boards. All right? Any other questions?
So you said you're the lab director for 221?
Yeah, all your labs.
Oh, really? Okay, cool.
Yeah, so whatever you want to do, just let me know. Better yet, if you have any suggestions you want me to do, you tell me. All right? Have a good day, everybody.
Cool. Thank you.